So in this video, we're going to be talking about the fundamental theorem of calculus and using it to evaluate a definite integral. So the objective today is actually twofold. So we are evaluating a definite integral. But we are using the fundamental theorem of calculus. So in a few short minutes, I have a lofty goal of both being able to explain what a definite integral is, being able to explain what the fundamental theorem of calculus is, and hopefully allowing you guys the tools to be able to evaluate definite integrals using this fundamental theorem of calculus. Now there's definitely a lot of overlap here. We have been talking about sigma notation as n is approaching infinity. The things we've touched on a lot of these topics before. The things that we're going to talk about today are going to tie a lot of that together in a nice bow and easier ways to solve a lot of the problems that we've been doing. However, sigma notations and limits as the intervals as n goes to infinity is a really, really important topic, and particularly when you're using much more of the advanced fundamental theorems of calculus. If you don't understand the sigma stuff, you're not going to be able to fully understand the power of the definite integral and what is going on with the fundamental theorem of calculus. So definitely the basis that we've been building up in class has been a good one to start at. Now just a quick review of what an integral is. Integral, we were also calling them anti-differentiation. Or integrals. And if you guys can remember the four main steps that we were using to solve these things, first off, we would be looking for a function f of x, capital F of x, and that would be the integral of lowercase f of x dot dx. Now the four steps we were using to solve these, hopefully you guys are really, really well versed in these. Our first thing, we wanted to rewrite them, which is algebra. Then we were going to integrate them. And this is using that table where, for example, x to the n would integrate to x to the n plus 1 over n plus 1 plus c. There's always that plus c that's involved. And the third step is we're going to simplify our answer. Once more back to algebra. And then our last step is just to check. And so, of course, we would check our final answer by taking the derivative of it, and if it equaled our original function right here, f of x, so if we take the derivative of capital F of x, so f prime of x, this should be equal to f of x, right? So we should be able to jump back to our original function. Now, let's jump into the fundamental theorem of calculus. So if we're starting with this, f of x is equal to the integral of small f of x dx, the fundamental theorem of calculus and I'm writing this big because it is hugely important. Fundamental theorem of calculus. Once again, underlying fundamental. This is one of the important things, one of the important take-home messages, one of the important take-home topics that you guys need to know by the end of this year or by the end of this class. And so basically what it is that if f is continuous, so I'm going to provide you guys with a definition here. And so it's going to be a lot in math speak. So it's got to be continuous on the interval lowercase a comma b. Once again, ab is a common notation for an interval. And we could also say f is an antiderivative on this interval, on the same interval, then here's the notation. We say b to a, the integral from b to a of f of x dot dx is equal to f of b minus f of a. Capital F of b minus capital F of a. Now I'm going to put a huge box around this, right? I'm going to make my box stand out like this because this is really, really important. There's a lot of calculus that's built into this, and it's really just a half a step more complicated than the stuff that we were talking about beforehand. So here, if we look at our definition up here, we've got capital F of x is just equal to the antidifferentiation or the indefinite integral of f of x over dx. So in here, we're doing the same thing, right? So we're starting with our f of x. We're finding what the indefinite integral is, which is still going to be capital F of x, but then we're plugging in b for one of them, and we're taking the same value and we're plugging in a, we're subtracting them, and that's what this is going to be equal to. So particularly yesterday, we were finding the area under the curve using sigma notation and limits as n was going to infinity. This is effectively giving us the same answer. All we have to do is take the antiderivative and then plug in the values at these limits or at these endpoints, subtract them, and we've got the area underneath our curve. Now this is hugely, hugely powerful, okay? I'll get to an example problem right away so that you guys can start understanding what in the world this is and how powerful it is. So first thing, let's start with an example. Say I'm giving you a problem and I'm asking you to evaluate this function. Now a lot of the notation that I'm going to use is pretty standard notation, so make sure you pick up on it and you're using it. If you take a calculus class, Calc 1, Calc 2, whatever it is in college, you're going to end up using the same notation, so make sure you're sticking with it. So, okay, so the problem is going to be to evaluate the integral from 3 to 1 of x cubed dot dx. Okay, and once again, what we're asking here is what is the area under the curve of this function x cubed from the interval 1 to 3. So we could go through the same steps we were doing with sigma notation where we could sketch it out, etc., etc. Now the first thing I'm going to do when I'm asked to evaluate this, however, is I'm going to take that antiderivative. Okay, so this doesn't need any rewriting. It's already in a good form to go right to our table. And if we have our table memorized and we realize that x to the n dot dx is going to be equal to, then I just jump right to x to the power n plus 1 divided by n plus 1 plus c. This is right from the table that we had that I gave out earlier in one of the previous sections. And so here we go. In this case, our n is going to be equal to 3, so I'm going to go ahead and just evaluate the integral. So I've got x to the 3 plus 1 divided by 3 plus 1 plus c. Now this c, I'm going to go ahead and leave it here, but you're quickly going to see how the c can just kind of go away in this case. So this is going to be equal to x to the 4th divided by 4 plus c. Okay, once again, I'm just going to keep the c there for now. And this is going to be our capital F of x, right? So our capital F of x is equal to this. Now if I look at the definition up here, capital F of x, once I find capital F of x, I can plug in these endpoints and figure out what the area underneath the curve is. So if this is my capital F of x right here, then I need to first plug in my first endpoint. And I'm going to do it, once you get good, you can do them really quickly, sort of in a line like this. But I'm going to do it just one at a time. I'm going to do it a little bit slow because you guys have never seen this before. So f of 3 is going to be equal to, now I'm just plugging in 3 for x, so 3 to the 4th power divided by 4 plus c. And then I'm going to also do the same thing sort of in parallel with f of 1, where I go 1 to the 4th divided by 4 plus c. Let me move my paper up here. So 3 to the 4th, let's see, that's 9, 81 divided by 4. So we end up with 81 divided by 4 plus c. And here we've got 1 divided by 4 plus c, 1 divided by 4 plus c. Exactly right here. Now we're not quite done yet. We've got my f of 3, I've got my f of 1. These are 2 endpoints from the original problem that I was given. So that's pretty great, because all I need to do, according to this fundamental theorem, is take the upper one, b, in this case it's going to be f of 3, and subtract the lower one, f of a, in this case that's f of 1. So I've got my f of 3. So now what I need to do is just to say that the whole integral, my answer is going to be f of 3 minus f of 1. And I've already got these figured out, so I can just plug them in. So I can say 81 divided by 4 plus c minus 1 divided by 4 plus c, right? So I'm taking the whole quantity of one, subtracting the whole quantity of the other. Now I'm super, super close to my answer. So 81 divided by 4, this negative sign gets distributed here, so I end up with 81 divided by 4 minus 1 divided by 4, which is just going to be 80 divided by 4. And then I've got c minus c. That's what this negative sign, when you distribute it, the c's cancel out. So I don't have to worry about the c's. So when you're doing definite integrals and you're actually evaluating these integrals at these endpoints here, you don't have to worry about the c's because the c's will just end up canceling. So here I just end up with 80 divided by 4, which is just equal to 20 units square. That's my answer. Now in the next video, I'm going to go through a lot more examples. Clearly this is a super powerful, super fast way of evaluating these integrals, and it's also, once again, really, really fundamental to calculus and how things are calculated.